Today, let's start with some open sequential logic device and their application. The first one, register. Register is two or more DP with common clock input. For example, this one, 1, 2, 3, 4. Okay, 4 DP. These 4 DP use common clock, use the same clock. That means when this clock tick, the flip-flop, this flip-flop, this flip-flop, and this one will read the data from the output at the same time. That means the output of flip-flops will update the data itself simultaneously. So this kind of device is called register. Okay. For example, for commercial IC, okay, the first one is 74175, and the second one is 174. Okay. For 175, there are 1, 2, 3, 4 internal flip-flops, and there are 2 active high and active low output for each flip-flop. For this one, it contains 6 internal flip-flops, but have only active high output. Okay. And for this one, 374. For 374, it contains 8 flip-flop inside, and there is output enable to control output. For example, this one. Okay. There is enable control input for each output. Namely, if output enable is 0, the enable input for each buffer will be active. That means the output from flip-flop can go out. But if enable output enable is 1, so each buffer will be turned off. Namely, this output will be disconnected or become high impedance state. Similarly, this one also, but this one inside is latch, not flip-flop. Okay, this one is D flip-flop inside, this one is D latch inside. Okay, the next often used sequential logic device is counter. Counter is any clock sequential circuit with state diagram contain a single cycle. Okay, something like this. The modulus of counter is the number of states in the cycle. So if the counter have, for example, have 4 states, then it's called modulo 4 counter, or divided by 4 counter. Okay. For example, this one is 4-bit binary counter. 4-bit binary counter. So there are 000 state, 001 state, until 11 state. So there are 16 state. 16 state. And each state, okay, you note from this state to this state, you count up, okay, or add 1, okay, increase 1. Okay. From this state to this state, okay, you add 1, right? It's count up, okay, or 1 increasing until become 111, and then it's back to 0 0 again. But well, how to design the counter? Someone may observe the behavior of the sequence of the counting number. For example, for LSB, it's 0 1 0 1 0 1 0 1. Okay. Change for every clock tick, right? When clock tick, change state, right? Then it's change from 0 to 1 and 1 to 0. Okay. Every clock tick is toggle, right? Toggle for every clock. And the next digit 0 0 1 1 0 0 1 1. Okay. Two clock tick and then change. Okay. Two clock tick and then change. For the next digit 4 clock tick, then change 4 clock tick and then change. Okay. Toggle for every 4 clock ticks. Okay. And MSB, okay, this one is 8 clock tick and then change the state. So if you know, okay, or you can determine the condition when this digit will change or toggle its value, that means you can implement the counter. For example, someone may note that if the previous digits are 1 1, that means when clock tick you will add 1, right? So carry out occur. Then it makes this digit change the number. Okay. If the previous digit 0 0 0 1 1 1 sorry 1 0, okay, no carry out to this digit. But whenever the digit is 1 1, that means for the next clock tick is add 1, right? So carry out occur, that means the value of this digit will change. Okay, if digit is 1, then change to 0. If digit is 0, then change to 1. So this digit also, okay, if the previous digit is 111, when clock tick, it change the value. Okay, and this one also 111, when clock tick, change 120. So by using this observation, so you can design something like this. Namely, for example, this one. Now I use T flip-flop with enable. So because the behavior of counter it does toggle, right, for each digit. You just know the condition when that digit toggle. Okay. So for example, this digit will be toggle. That means enable will be 1 when the previous digit is 1, this one, all 1. So you just add Q2 and Q1 and Q0 together. If this three digit is 1, that means enable is 1. That means when clock tick, check the condition in input condition, enable is 1, so it's toggle at Q3. Okay. For Q2 also, okay, this enable will be 1 when the previous Q1, Q0 is 1 1. Okay, it's 1 1. So Q2 toggle if this condition become true. Okay. Q1 also, and this is for this one is counter enable. Okay, the counter will be enable, will be active. The circuit will be active if enable signal is 1. Anyway, if someone cannot observe the behavior, what should you do? Okay, you may write something like this. For example, If I start from this state, then I follow this one, Q3, Q2, Q1, Q0. Q3, Q2, Q1, Q0. It is the current state. Maybe 0, 0, 0, 0. Okay. And then the next state is 0, 0, 0, 1, 0, 0, 1, 0, 0, 0, 1, 1, 0, 1, 0, 0, 0, 1, 0, 1, 0, 1, 1, 0, okay, and so on. And 0, 1, 1, 1, and the next one, maybe I can copy this one, 1, 1, 1, 1, 1, 1, 1, 1. Okay, let's do this to set the time. Okay, this sequence. Okay, and the next state, okay, when clock tick, it change to Q3 star, Q2 star, Q1 star, and Q0 star. So it changed from what? 0, 0, 0 when clock tick, it go to 0, 0, 0, 1, right? And from 0, 0, 1, it's go to 0, 0, 1, 0. And the next state of 1, 0, 0, 1, 0 is 0, 0, 1, 1, okay, and so on. So let me copy from this. Okay, maybe this one. Okay. And for 1, 1, 1 state, the next state is 0, 0, 0, 0. Okay. So if I use T flip-flop with enable, that means each flip-flop, okay, each flip-flop have enable, right, and clock. If enable is 1, when clock tick, Q will change to, okay, the new value of Q will change to invert of Q, right? It's toggle. Okay. If enable is 0, when clock tick, nothing change. Q star equal to Q. Okay. So now you just determine the value of enable. So because there are 4 flip-flop, that means you have 4 enable signal that you should determine about each value. Enable 3, enable 2, enable 1, enable 0. Okay, so you just consider if this chain 0 to 0, I consider this one Q3. Okay, consider just with Q3 to Q3 star. That means enable 3 will be 1 if it's chain, right? 0 to 1 or 1 to 0. This one not chain, right? 0 to 0 not chain, not chain, not chain. Okay, that means enable is 0, 0, 0, 0, 0, 0 until this state, right? This state is saying 0 to 1. So this state enable is 1. And 0 and it's not change, 1 to 1 not change, that is 0 at here, 1 to 1 not change, so at here 0, 0, 0, 0, 0 until this state. Okay, change 1 to 0, so it's 1. Okay, after that you may use key map, right, to determine the function of enable 3. For example, this one, and then write it here. this one. Q3, Q2, Q1, Q0, right? And the value for it is 00, 01, 11, 10, 00, 01, 11, 10. And for enable 3, B1, for the state 0, 1, 1, 1. Q3, Q2 is 0, 1, Q1, Q0 is 1, 1. This cell, and this state is 1, 1, 1, right? 1, 1, 1, this one. After that, you can select this group for clear. So you obtain its go to Q2 and Q1 and Q0. Okay, something like this. For enable 2, enable 1, enable 0 also. Okay, you just find out. Okay, the condition when enable will be 1. Okay, so okay, after that you know the equation, so you can draw the circuit diagram, and the result will be this one. Okay, this one or this one. Okay, the difference between this and this is for this one, for example, for this one, okay, we use 3 or 4, right? 4 input AND gate to AND Q2, Q1, Q0, and counter enable directly. Okay, but the top one, okay, Q2 and what? And output of this AND gate, and this AND gate you AND between Q1 to this output of this AND gate, which AND between Q0 and counter enable. Same function. That's only use multiple input AND gate or use only 2 input AND gate. Okay, if you use this one, okay, this enable signal will be available. You must wait for 1, 2, 3, right? 3 propagation delay time of these 3 AND gate. But this one, okay, may be faster, right? Because the signal from Q2, Q1, Q0, okay, connected to this input AND gate. Okay, for this one is called parallel. Okay, but this connection is serial, so it's called synchronous serial counter, and this one is synchronous parallel counter. Okay. And one more IC counter that often used is 163. Okay, it's a 4-bit binary counter. How does it work? At first, there are control input: enable, load, and clear. Okay, the function follow this table. For example, if clear is 0, when clock tick, okay, it will change to 0, 0, 0 state. Okay, not depend on the current state. This x may be 0 or 1, right? 0 or 1, x, okay? Don't care, okay? So, how does it work? Okay, for example, when clear is 0, okay? When clear is 0, this output will be 1, right? 1 at here, 1 at here. The output of this AND gate with active low input, the output will be 0. This one also output is 0. So this part of the circuit will be 0 to this and this. And this output will be 0. This output also 0. 0 or 0 is 0. That means now Now 0, okay, data 0, you wait at D. So when clock tick, and this flip-flop, you read data from D and update with 0. Okay. For flip-flop, QB, QC, QD also. All of this, when clear is 0, there are 0, 0, 0, 0 waited here. Okay, just wait for clock tick. Then you update data with 0 for every bit. Okay, and if clear is 1 and LD is load. Okay, load function, and load is active load. So when load is 0, what happened? When clear is 1, inverter, then it's 0 at here, 0 at here, 0 at here, then output is 1. Okay, 1 and 0. Okay, then this output become 0. That means now 1 at here, 1 and data A. So it's become A at here. For this one is 0, this output is 0. So A and 0 is A. That means now, the data from A will go to D. Okay. Similarly for B also. B will wait at here. Data from C go to here. D also. Okay, flow and wait at here. B, C, D. Okay, B, C, D is external input. Okay? It's data input. Okay, if you understand, IC is this one. Then when clock tick, all people you read data at the same time. Okay, because using common clock. So when update to A, update B, the value becomes C and D. So this kind of behavior that read the data at the same time is called load. Okay. And what else? If not clear, not load, that means you must apply 1, 1 at here. So what happened? 1, 1 at here is 0 at here. This output is 0. Then 0 at here, this output is 1. That means the data, this one is 0. Then this output is 0. And this is become 1. Okay, that means data from here. Okay, we will feed to here. This one also. This one also. Okay, this one also. Okay, let's consider this one. For this one, this one is connected to output of this XOR gate. This one is active low. Active low, you can cancel them and treat it as QD. Okay, QD. And another input of this XOR is come from what? The one is enable P, enable T and together. Okay, this is enable. And with what? QC, right? This is active flow QC, but this is also active flow. So it's and between QC, this one, from QB, and the last one from QA. So if QC, QB, QA is 1, 1, 1, that means this output is 1, and if enable is 1, so it's 1 at here. 1 XOR QD is become QD prime. Okay, toggle occur. But if this condition is not 1, 1, 1, so this output is 0. Or if enable not active, is 0 at here, so this output will be 0. Then 0 XOR QD become QD, okay, nothing change, okay, for another bit also. So it is the detail about the mechanism for this counter. Okay, how to use this one? For example, the easiest one is free running counter, running without any condition. That means it can count from 0 0 0 0 until 1 1 1 1 and repeat 0 0 0 again. Okay, how to connect it? Okay, if don't do it clear, don't you low to connect to high. Okay, logic 1. And enable P and enable T must be high both. Okay, just then you wait for clock tick, then you update for every clock tick, and the result is something like this. Okay. Oh, one more. Output terminal is RCO. What is RCO? Look at here. RCO is the output of this AND gate, right? It's AND between QD, QC, QB, QA, and enable T. So if the current state is 1 1 1 1, or the last value or last state of the counter, so RCO will be 1. Okay, it has an indicator to take that now the counter is last state or not. If yes, okay, if QD, QC, QB, QA is 1 1 1, so RCO become 1. Okay, if not, RCO is 0. Okay, for the next page is show another ICs. Okay, counter IC. Some is modulo 10 counter, namely it's count from 0 to 9, and some is binary counter, 4-bit binary counter, then it's count from 0 to 15. Okay, and some IC okay have asynchronous clear, some is synchronous clear. For synchronous clear, okay, when clear active, namely maybe apply 0, and the circuit will feed 0 0 0 0 at data input of the flip-flop, but the output Q, QD, QB, QC, QA not become 0 suddenly. It must wait for clock tick, right? This kind of behavior is called synchronous clear. But if this clear do not connect directly to clear of is D flip-flop. That means when this clear is 0, so clear terminal of each becomes 0, and then we will make output of flip-flop change to 0 suddenly. Okay, need not to wait for clock. Okay, this kind of clear is an asynchronous clear. Okay, asynchronous clear is different. And the next page that shows some application. For example, if I want to count from 5 to 15, 5 is 1 0 1 0 1, then I connect this one 0 1 0 1. Okay, and when the circuit this counter count to 1 1 1 1, RCO then become 1. Okay, and we use this signal, okay, to be the condition to load, namely because load is active load, then I add 1 inverter at here, so it's change 1 to 0. When load is 0, that means when clock tick, it will load or read data from input A, B, C, D at the same time. Then it's update to 0, 1, 0, 1. Okay, that means when it count to 15, it will back to 5. Okay, when it's back to 5, R0 not 1 is 0. And this output of inverter is 1. So now this load signal is 1. That means now it's back to normal counting mode. Okay, not low. So that means when clock tick, it will count up to 0, 1, 1, 0, and clock tick again 0, 1, 1, 1, okay, and so on until 2, 1, 1, 1 state. Then RCO become 1 again, and then you load. Then you load the next state is from the CBA we connect to 0, 1, 0, 1 or 5 again. Okay, for this one, it checks that this bit is 1 or 1 and 1 or not. Okay, if this bit is 1 at the same time and together, this output will be 0, and you go to clear. That means if it count to 1 and something 1, okay, if you look on this sequence, okay, this one is better. Okay, that state that MSB is 1 and the next this is 1. When you count up from 0, 0, okay, you count up, and the first state that this bit is 1 and this bit is 1 is this state 1, 0, 1, 0. Okay, and then if this condition become 2, then it's back to 0, 0, 0 by using clear, okay, to reset all flip-flop output. Okay, then using this one to check the condition this bit is 1, 1 or not. If yes, it will clear the output. Okay, and don't forget that this number is synchronous clear. That means it's not become 0 suddenly. It must wait, right? Must wait for clock tick. Then it will go to 0, 0, 0, 0 after clock tick. So it will count from 0 to 10. Okay, 0, 0, 0, 0 to 1, 0, 1, 0, and back to 0, 0 again. And for this one, it's similar to the previous one. It just take 1, 1 or not. Okay, the first step when you count up is that this bit is 1, this bit is 1, is 1, 1, 0, 0. After that, you go to load, and when load, it read data from this one 0, 0, the CBA 1, 1. So when clock tick, we load the new data from the CBA, so it's become 0, 0, 1, 1. Okay, after that, if when clock tick, this bit is 0, 0, not 1, 1. That means this output is 1, not load. Okay, now it's in counting mode. So when clock tick, we count up to the next state is 0, 1, 0, 0. When clock tick again is 0, 1, 0, 1. Clock tick again 0, 1, 1, 0, until go to state of 1, 1, 0, 0. Then this condition become true. This output become 1 again, and then we will load the next state from the CBA. Okay, this input. So it's go to 0, 0, 1, 1 again, and repeat this one. So it repeat between 0, 0, 1, 1. Okay, 0, 0, 1, 1 to 1, 1, 0, 0. Okay, or 3 to 12 in decimal. Okay. By the way, if you want to count greater than or more than 1 and more than 4 bit, you may use, for example, if you want to count 8-bit counter, okay, you can use these two ICO2 modules connect together by using RCO. RCO connect to this enable, and maybe use command clock, command clear, and command root. So if the counter start from, for example, 0 0 0 0, this one also 0 0 0 0. Now RCO to be 0, right? When clock tick, if this enable is 1, so it will count up to 0 0 1. Okay, but this one is enable is 0. Okay, then nothing change. That means it still be 0 0 0 0. Okay, when clock tick, you count up to 0 0 1 0. Okay, this will not change. It's 0 0 0 again until it's go to state 1 1 1 1. So RCO become 1. That means when clock tick, enable active. Now it go to 0 0 0 1. Okay, count up. Okay, so you can use this configuration to extend. Okay, extend the counter from 4 to 8-bit counter. Okay, and for this page, just show you some example. For example, if you use counter to count, this example you use 3-bit, right? As the result of counter, and you use decoder to convert binary value, 3-bit binary value to 1 out of 8. Okay, only 1 bit active. Okay, at the output. So what happened if I start from 0 0 0 0 0 0? That means now Y0 active. Okay, this one is set is this output is A0. Okay, active low. That's state 0. A0 is 0. Okay, active low, and another bit not active. That means it's high. And now when clock tick, this one change from 0 0 to 0 0 1. Then Y1 active. Okay, so state 1, Y1 active. That means the output will be 0 at here and 1 1 1 for enter bit. And now what happened if it count to from 0 0 1 and count to the next 0 1 0. Okay. So Y2 should be active, right? Should be something like this. Okay. Anyway, when it change, to be changed in this example, this bit 1 change to 0 and this bit 0 change to 1. It may have different propagation delay time. That means if this bit change faster, what happens? Then if you go to what? Okay, if this bit change faster, 0 0 1. If this bit change faster, that means it go to 0 0 0 first before this bit change to 1, right? That means at this point of time, Y0 will be active. This one, okay, it's glitch. Okay, or if this bit change faster, what happened? So from 0 0 1, if this bit change faster, so it's 1 at here, this bit still be 1, okay, and 0, and wait a little bit, this bit change to 0. Okay, this is 1, it's 0 at here. So now this point of time, it make Y3 active, right? 0 1 1. So this point of time is maybe have glitch at here, okay, at this bit or this bit, okay, S0 or S3. based on which bit is changed faster. Okay, maybe occur. Okay, if you don't want glitch occur, okay, what should you do? Okay, you may use D latch or D flip-flop. Okay, let's use this is when you use, oh sorry, use D flip-flop. Okay, use D flip-flop because when clock tick, right? When you use D flip-flop, the signal that feed to D flip-flop, okay, will be not read and update at the output suddenly, right? It's not wait for clock tick. That means when clock tick, for example, in this case, when clock tick, okay, the signal already go to the steady state. That means the glitch already disappear. So you can be sure that this final output have no any glitch. Anyway, you must wait for more one clock tick. Okay. Okay. The next CPU device is chip register. Okay. For chip register, for example, this one. Okay. For example, if there are, okay, let's add this one. Four D flip-flop, right? Use common clock. That means all of these flow flip-flop will change or load data at the same time. If I connect this output to the next input of flip-flop, this output connect to next flip-flop input, and this output connect to next input of flip-flop. So what happened? Assume that the current value of each flip-flop is A, B, C, D. Okay. When clock tick, if this data is E, that means this flip-flop, you see the data at here as B, right? It's B, right? And this one read data from this flip-flop or C. Okay. And this one read data from this flip-flop or value of D. And for this one read E, right? So when clock tick, you change to B, C, D, and E. So note, the data will shift, right? Shift from here to here. Okay. This kind of behavior is called shift register. Okay. So the data from this one is shift to this one shift to this one shift to this one. Okay, and this first one we read the new data from serial in. Okay, this is serial in. Okay, and if you use only one bit output, then it becomes serial out. Okay, go out one bit for each clock tick. But if you use multiple bit output, that means when clock tick, you can use 4 bit at the same time. This kind of output is called parallel out. Anyway, you cannot use this output for every clock tick. For example, if the current value is something, okay, unspecified something, and the first clock tick zero is A, that means when clock tick is A, this one go to here, this one go to here, this one go to here, and A come here. Okay, become A here, A X X X, and the next clock tick if the value at 0 is B. That means when clock tick, A go to here, X, X, and B come here, right? And if the next one is C, so when clock tick, A to here, B shift to here, and C at here. And the last one, if the next clock tick, the value of 0 is D. So this one read data, C is as A. This one, C is input data as B. This one read data from here as C. So when counting is changed to here, this one read D. Okay. Okay, now you see that the output of this four bit from the flip-flop. This one is same as this one. Okay, this one is serial in. Okay, enter to the circuit. Okay, 1 bit for each clock tick. But this output, okay, you can take all of these 4 bits at the same time. Anyway, you must wait for 4 clock tick before these 4 bits become B, A, B, C, D, or the same as your serial input. Okay, so you can use this one to convert serial to parallel. Anyway, the rate of data that you can use is not the same. Okay, the output frequency may be lower than input frequency for the data rate. Okay, and this one actually it's quite the same. Just different that you use only single output or multiple bit output. If you use single one, it's serial out. If you use every bit at the same time, it's parallel out. Okay, and for the input part, okay, you can use both chip mode or load. Okay, that means you can use data only 1 bit from serial in, or use data from this data input load simultaneously or at the same time. Okay, how does it work? For example, if you use signal, this one is as 0. So what happened? This output is 1, right? Then 1 and 0 in is become 0 in at here, 0 in at here, and 0 at here, right? 0 at here. Then output is 0. 0 or 0 in is 0 in. And another one, this output is from this. Okay, that means output from the previous flip-flop go here, and this one also. This one is this one. Then data from here go here. That means when clock tick, okay, you shift, right? Shift data from this one to this one, from this flip-flop to this flip-flop, and 0 in update to this one. This is shift mode. Okay. For load, you apply what 1 at here. This will become 0. That means 0 and anything becomes 0 at here, 1 at here, 1 and data D is become 1D at here. For this one also, it's 2D and ND. Okay, this one is 0, 0. So 1D or 0 is become 1D. Okay, 2D or 0 become 2D. Okay, ND or 0 is ND. That means the external data input will feed to internal D flip-flop, and we will update simultaneously when clock tick. This is load. Okay, operation. Okay, and for this IC is universal chip resistor. That means you can use both chip left, chip right, hold and load for this table function table. Namely, if the control input S1, S0 is 0, 0. When clock tick, nothing change. QA starts to be QA, QB starts to be QB, QC star still be QC, QD star, still be QD. Nothing changed. Hold mode, okay, or hold function. But if S1 0 is 01, okay, data will ship, okay, it's ship right mode. Namely, data from A, you go to QA, go to QB, QB go to QC, QC go to QD, like this. Okay, and for the portion of QA, okay, it receives data from external input R in, okay, chip right mode. For chiplet, S1 is 1, S0 is 0, okay, it's changed to this direction, and this portion will read data from L in. L in is that here. Okay, for chiplet mode, you apply 1 at here, 0 at here. Okay, the flow of data will shift in this direction. L into QD, QD to QC, QC to QB, QB to QA. For chip right, apply 0 at here, 1 at here. Data will shift from R in to QA, QA to QB, QB to QC, QC to QD. And for load function, you apply 1, 1 to the S1, S0. Okay, and the data will update with A, B, C, D, namely from external input A, B, C, D. Okay, now for this one, just show internal circuit of this IC. Actually, it uses multiplexer to select which data should feed to the input of flip-flop. For example, if S1, S0 is 0, 0, okay, this one active. Okay, this one will be active, namely this output will be and from what? This one. Okay, this one. Output itself, okay, will feed to the input. That means when clock tick, will update with the same value. So nothing change. It's hold mode. Okay, not change. But if S1 is 0 is, for example, is 0, 1, 0, 1, the signal from QA, data from QA will go to input of QB. That means when clock tick, okay, value from QA will update to QB. Okay. For 1, 0 also, okay, this one go to here, maybe from QC. And 4, 1, 1, okay, you load data from external input, okay, this one, 1, 1 to internal flip-flop. Okay. Of this at the same. Okay. Okay, this is universal, okay, chip resistor 194. Okay, now let's form some application for this chip register. Okay, let's use it as counter. Counter means if you draw the state diagram, the state will change with maybe single circle. For example, the first one is ring counter. We show you the result of 4-bit ring counter. It may start from 0, 0, 0, 1. When clock tick, it change to 0, 0, 1, 0. When clock tick, change to 0, 1, 0, 0. When clock tick, change to 1, 0, 0. Okay, and then repeat this one. This is the ring counter. If you write state diagram, it's something like this. This one. Okay, if I want to design, what should I do? Okay, maybe use this one. Okay, if I start from Q3, Q2, Q1, Q0, okay, the state maybe start from 0, 0, 0, 1, right? When clock tick, it change to Q3 star, Q2 star, Q1 star, Q0 star. Okay, the next value of this state is 0, 0, 1, 0, right? And the state there are 0, 0, 1, 0, 0, 1, 0, 0, 1, 0, 0, 0. Okay, the next state of this state is what? 0, 1, 0, 0, right? And for this one, go to 1, 0, 0, 0, and this one back to this one, 0, 0, 0, 1. Okay, so now you just find the relationship between each bit of the next state. Okay. So at the first, for Q3, you see that it's same as Q2, right? And Q2 same as Q1. Okay, Q2 star same as Q1, and Q1 star same as Q0 star. That means it's right. That will form Q2 to Q3, right? Okay, Q1 to Q2, Q0 to Q1. It's chip left. Okay, chip left. That means you should apply S1 and 0 as 1, 0. Okay, 1, 0 for each state. Okay, okay, you can apply constant value with 1, 0 for chip left mode. Chip left. And how about L in? Okay, for chip left, that means you will use L in, right? Okay, okay, L in. For L in, if you use connect back to this one, if you connect Q3, Q2, Q1, Q0 to QA, QB, QC, QD, QA, connect to QA, QB, QC, QD, right? For each flip-flop. That means if you use L in you go to QD, right? Go to QD. So from QD, okay. So let's know. So if you consider this one, what the value of QD or Q0 star, right? Okay, QD star or Q star. Okay, let's say. Okay, it receive from L in. So take a note. It's same as Q3, right? Okay, Q3. Okay, same as Q3. 0, 0, 0, 1. Okay, then you must connect L in equal to Q3. Okay, so your connection will be used chip register. Okay, this one. Okay, this IC. Okay, you connect Q3. Okay, to L in, and you connect. Okay, S1 as well as chip left mode. 1 at here, 0 at here. Okay. Anyway, to set the initial state value, let I connect reset at here, namely when reset is 1. Now S1 is 1, so it's load, right? Load. That means we wrote data from A, B, C, D. Okay, we wrote initial state with 0, 0, 0, 1. Okay, connect to ground 0, 0, 0, and connect to 5, 4, 1. After that, when you apply 0 at this is 0. So now it's shift left mode. Data from LN you go to QD, QD to QC, QC to QB, QB to QA. So you can complete this ring counter. Okay. By the way, if you take a note, there are 4 states, right, for ring counter. And your initial state maybe start from 0, 0, 1. What happens if your state is, for example, if your state go to 0, 0, okay? When clock tick, the next state still be 0, 0, 0, right? It cannot back to the normal state. Okay, it's not so good. So what should I do is if I want to make the circuit back to the normal state, okay, someone may send reset signal again. Okay, one at here, then you load data initially, okay, from this input 0, 0, 0, 1 again. If you don't want to reset every time when the circuit go to abnormal state or unused state, what should you do? Okay, you can do something like this. You should design the next state for unused state to some normal state. For example, this one. From this one, I use this AND gate, okay, with active flow input AND gate to check that the state of counter is 0, 0, 0 at Q2, Q1, Q0 or not. Okay. If yes, the next state should go to what? Okay, if this condition come true, this output is 1, Lin is 1. The next state you go to 0, 0, 0, 1. Okay, for example, I use this one. For example, if now the state is something x, 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 which may be unused state or abnormal state. So if this condition is not true, not 0, 0, 0, okay, so this output becomes 0, right? Okay, when shift left clock tick, this shift to here, then x, x, x at here, and read data from here to here. So it become 0 at here. Now assume the condition 0, 0 still be not true. So this output is 0. When clock tick, then it shift 0xx to here, 0xx to here, and read data from Lin to here. So now it still be 0. If this x00 is not is condition not true for this AND gate, that means output still be 0. And now when clock tick is go to 0, 0 at here, right? Now this condition come true, right? That means if clock tick again, you feed this logic 1 go to the next step at this position. Okay, and this 0, 0 you shift to here. So 0, 0, 1 is one of the normal state. Okay, something like this. So this kind of condition is called self-correcting ring counter. Namely, if your machine go to unused state, okay, you just wait for some clock tick. It can back to normal state by itself. Okay. Another one application is this one is Johnson ring counter, okay, or twist ring counter. Johnson ring counter. Oh, something lost it here. Johnson, okay, ring counter or twist ring counter. Twist ring counter. Okay, the put one is something like this. At initial state maybe 0, 0, 0. Okay, when clock tick, 001 when clock tick, 0011 when clock tick, 0111. Okay, the output will turn on. Okay, for uh, for each clock tick. Okay, more one bit will be turned on, and when it's full to 111 when clock tick again, we turn off one bit for each clock tick. Okay. So harmony state of this one. Okay. Let I write the result. Maybe at here. For Q3, Q2, Q1, Q0. If initial state is 0, 0, 0, 0. Okay. When clock tick, and the next state is 0, 0, 0, 1, 0, 0, 1, 0, 0, sorry, 0, 0, 1, 1, 0, 1, 1, 1, 1, 1, 1, 1, 1, 1, 1, 0, 1, 1, 0, 0, 1, 0, 0, 0, and back to 0, 0 again. Okay, there are 8 steps. Note that there is no separation between 1, logic 1 or logic 0. Okay, this will be adjacent together. This one also. Okay, now the next state when clock tick, the value of Q3 star, Q2 star, Q1 star, and Q0 star. Okay, now you just take a note of the relationship between this one. Okay, it's equal to, okay, let's copy this one. Okay, from this. And the next state of this is what? 0, 0, 0. So we see that Q3 star, Q3 star, Q3 star, same as Q2. Okay. Again, Q2 star, same as Q1. Okay. Q1 star, same as Q0. Okay, it's triplet, right? And how about Q0 star? Q0 star 1, 1, 1, 0, 0. But Q3 is 0, 0, 0, 0, 1, 1. It's opposite, right? So now you can write equation for each next state, right? Q3 star is Q2, Q2 star is Q1, Q1 star is Q0. Okay, Q0 star is Q3 prime. Okay, inverse of Q3. So based on this condition, you can implement the David swing counter or Johnson counter by use inverter. Okay, connect from Q3 and feed to L in. Okay, that's all. And note for this counter, there are 8 states, right? And each state there's no any separation between 0 bit or 1 bit. Okay, that means it's very easy, okay, to check the state. For example, if you want to check its state S3 or not, you just check where these 2 bits, that's enough, right? Namely, Q2 is 0 and Q1 is 1. Okay, you use this condition to check. Okay, need not to check all bit. Namely, you need not to use Q3 prime and Q2 prime and Q1 and Q0. Okay, you can reduce, okay, the parameter or variable to check that state. Or if you want to check S1 or not, you just check that and this MSB and LB is 0 both or not. If yes, okay, the bit between this one must be 0, okay, right? So you check only this bit and this bit, that's okay. So the condition is Q3 prime and Q0 prime, okay. For for H5 state 5 also, okay, just check this one. This test Q3 is 1 or not, Q0 is 1 or not. That's enough. Okay, again, if you connect just with this one, it's possible, and see maybe go to some undo state. For example, 1 0 1 0. Okay, you do this one, you repeat between 0 1 0 1 and 1 0 1 0. Okay, cannot pop, go back to the normal state. So if you want to do self-correcting, okay, you may use something like this. For this example, I just show you to check the condition is the state that Q3 is 0 and Q0 is 0 or not. Okay, it's similar to this state, right? It's similar to state S1. Okay, if yes, the next state should be 0 0 0 1. So if this condition come true, 0 at here, 0 at here, then if we to S0 to be 1, S1 already connect to 5.4 or logic 1, so it's become load function or load mode. So it will read data from A, B, C, D. And the next state that you want to be is what? Is 0, 0, 0, 1, right? So you must connect A, B, C, D with 0, 0, 0, 1. Okay, that's all for make the self-correcting. Okay, now the last topic, okay, and the main topic for today is algorithmic state machine design, okay, ASM. Okay, to decide this one, actually from the previous lecture, you can design state machine, right, by using this structure, namely flip-flop, right? Flip-flop, maybe 1 2 3 flip-flop, okay, based on number of states, right? And for the simple one, let's use D flip-flop. Okay, the flip-flop will change the state, okay, when clock tick. And for clock synchronous state machine, we use common clock, namely all flip-flop, okay, connect to the same clock. And when clock tick, you read data, right, from circuit F. Okay. Circuit F, or it is combinational circuit, right? Combinational circuit with read data from external input and from what? From flip-flop. Okay, maybe Q1, Q2, Q3, something like this. Okay, from this flip-flop. And output of flip-flop, okay, maybe change something to be the final output by using circuit G. Okay, circuit G also combinational circuit. Okay, and the previous lecture is something like this. Anyway, for the big system, okay, it's not convenient. Okay, it's quite hard to design by using only this configuration because maybe it's many output and many complicated, okay, operation. So to design, then we will separate into two parts. The first one is control unit. Okay, the control unit we will use normally we will use the same structure as flip-flop, circuit F, and circuit G. Okay, that you studied previously. But another one is data path. Data path maybe using some register, some counter, okay, to process the data. The control unit, okay, will control when to control the device or element in data path or data unit. Okay, when we ship the data, we will load the data. Okay, something like that. Okay, that's the example. Okay, to decide this one, okay, you need to draw something like flowchart, but it's not flowchart. Okay, for the software design, right? This one is called AAM chart. Okay, AM chart. The difference is AM chart it will work repeatedly. Okay, until power off. Namely, if your circuit have power supply, it will work all time. Okay, at the end. For the software, something you start, right, and do something. Okay, maybe have some decision, yes, no, and end, right, and end. But for step machine or AM chart, that there is no this stop. Okay, and because AM chart is based on state machine, right? For each state, okay, we will complete process within 1 clock. Okay. Okay, to write down the AM chart, okay, you need to know its component of state box, decision box, and conditional output box. Okay, something like this. Okay, let's see for each one. For state box, okay, every state, okay, must have state box. We draw it with rectangular, okay, and show something inside the box. It may be register operator to assign or clear or load data, okay, to the register, and some output that depend on the state, namely more type, right? More type output. And sometimes we write state name at here and binary code of this state, okay, at this corner. And for decision box, okay, we use this one, okay, this diamond, okay, shape, or this shape, okay. For example, this one, for decision box, it shows the input value, okay, condition by using input variable that is 0 or 1, okay. If this condition come true, go to this state, okay. If this condition come true, go to this state, okay. The next step based on input condition. For example, this one, if x is 1, if y is 1, go to state B. If x is 0, go to state A, okay. Or if x is 1, y is 0, go to A. Of course, you can check y first and then check x. Or actually, you can check both at the same time, okay. It not affect because the state will change when clock tick. And you must do this condition checking completely before clock tick, right? So it's not important, right, to check y or x first, okay, because it gives the same result. And the next one is called conditional output box, okay. This output, okay, based on the input value, namely is mirror type. Okay, mirror type output. For example, this start is input variable. If the value of start is 1, so it prepare to do this operation. Namely, we clear, okay, or assign 0 value to register PC. Okay. One thing that you should be careful for register operation. For example, this one. Okay. Now just to prepare, okay, to clear register, okay, or load data 0 to R. If you, if I back to, for example, this one, this chip register, or enable counter, something like that. Let's select one of these. Okay, for example, this one. For example, this one. If you want to clear, right? If you want to clear, you must apply logical signal at here, right? 0. But the state, okay, or the value of a register or counter not clear suddenly. It must wait for clock tick, right? Okay. Or if you want to count up, it just send 1 to enable of the counter. But it's not count up suddenly. It must wait for clock tick. Okay. So for this state, sorry, for this one, okay. For this one, just apply something like enable signal or clear signal or low signal, okay, into the counter or register. But okay, the value not clear or not load suddenly, right? It must wait for clock tick. Okay, this point is very important. Okay, now example for this one. Okay. Okay, for the timing, all of this is the same state. Okay, and let's say this state is state idle. Okay, this state name. State name. Okay, at this state, the output available eval is active. For active output, we write it here. Or sometimes you may write it equal to 1, something like this, if it's active high. Okay, and then we take the input start. Okay, input start is 1 or 0. Okay, if start is 0, okay, when clock tick, it will back to idle state again. But if start is 1, okay, it's prepared to clear register A. Prepare to clear register A. And when clock tick, if Q0 is 1, it go to state mod 1. If Q0 is 0, after clock tick, it came to mod 0. Okay, this is the condition, input condition. So if you look on this timing diagram, okay, this one. Okay, now start. Okay, start. At state idle. At this state, eval is 1. Okay, right. Eval is 1. It's high, right? And register A have some initial value, okay, or previous value. So now clock tick at here, start is 0. Clock tick start is 0. That means it's go to state idle again. Okay, state still be idle. After this clock tick still be idle. Okay, and now if start change to 1, and at this clock tick, now the step between X start is 1, okay, Q0 is 1, so go to here, right? So it go to state -1, okay, state change to -1, and this state in state box write nothing. That means there is no any active, no any output active. So output eval change to 0. Okay. Same thing, you can write eval is 0 at here, and it's 1 at here. In practical, many systems have many output. So it's not convenient if you write down every output that to be 0 or 1, right? So often we write just only active output in the state box. Okay. If that output is not in state box, that means that output is not active. Okay, and okay, after clock tick, okay, this one, and this one clear. Okay, clear signal, maybe 0 or 1 is active, right? But not clear. Register A suddenly is must wait for clock tick. Okay, that means when clock tick, value of register A becomes 0, 0, 0. Okay. And now, okay, if you understand, let's practice. Okay, something about the ASM chart. Okay, example 1, odd parity checker. Okay, your circuit maybe have one input X and one output Z, as with active high. Okay, okay, if when clock tick, the first value of X is 0. Okay. Now this circuit is odd, right? To check that number of logic 1 is 1, is odd or even. Okay, the first one is 0. Number of logic 1 input is 0, so it's not odd, right? Output is 0. And if the next input is what? Is 1. Now total number of 1 is odd. Okay, now output is 1. If the next input is 0, okay, total number of 1 still be 1, so it's odd, so output Z is 1. If the next input is 1, now total number of logic 1 input is 2 or odd, so now it's even. Okay, it's even, right? So output Z now change to 0, something like this. That means if I write the AM chart, is something like state even, no any output active. State odd, output active. Okay, active high, then its value is 1. So at state even, if input X is 0, it still be state even after clock tick. But when clock tick, if X is 1, it's go to state odd, right? At state odd, if input is 0, it still be odd state. But if X is 1, it's go to state even. Okay, that's all. Okay, so now if you can write down the aim chart, of course you can design the state machine. For example, for this one is because there are 2 states, that you can use only one state variable, maybe only one flip-flop. Okay, in this case I assign 0 for state even and 1 for state odd. Okay, this is a state assignment for these 2 states. So okay, let me write down state output table from here. State even, when input X is 0, still be even. Okay, or if the present state or current state is odd, If input is 0, next state is odd. When x is 1, it change to even to odd, change odd to even. Okay, and this state odd output active. So now I think after the state assignment, assign q equal to 0 for state even, and q equals 1 for state odd. So when I apply this, so after that I can design this one, right? From this, based on this one, q star related with q and input x with this one, right? Okay, namely is q star equal to q prime and x. Okay, this one and this one is become 1 when q is 1, x is 0. So is this q and x prime, or q xor x. Okay, this is for q star, and output z equal to q. So your circuit maybe, if you choose D flip-flop, maybe something like this. This is q, okay, xor between x not input x and q. Okay, and your output is q, so this is output z and clock. Okay, that's all for odd parity checker. Okay, the next one to show how to convert, okay, from state diagram to M chart or M chart to state diagram. For example, this one is a mirror type state machine, right? This one. Okay, F is input, Z is output. Okay, input, output. For example, at state A, at first, because there are 3 states, so I use 2-bit for these 3 states. I assign 00 for state A, 01 for state B, 11 for state C. And then at state A, when input is 0, output is 0. Okay, at state A, when input X is 0, output Z is 0. When clock tick, if X is 0, is go to A, right? Then go to A. At state A, if input is 1, it go to state B, right? Input is 1, go to state B. At state A, input is 1, output is 0. Output is 0. Okay. Now at state B, if you go to C, if input is 1. Okay. At state B, if input X is 1, go to C. With output Z is 0. And if input X is 0, it's back to A, right? 0, and output is 1. Okay. Note the output depends on the value of X, right? If X is 0, output is 1. If X is 1, output is 0. Okay. It's mirror type output. And the last state C, okay, you go to B when input is 0, and go to A when input is 1. Okay, X is 0, go to B, X is 1, go to A. And for this one is more type state machine. So you can write output in the state box like this, namely at state A, state C, output Z is 0. At state B, output is 1. And for the state change, when input is 0, when X is 0, go to A. When X is 1, go to B. X is 1, go to B. At state B, when input X is 0, go to C. x0 go to C. When input x is 1, go to A. And state C, when input x is 1, go to B. At state C, when input x is 1, go to B. And when input is 0, go to B. And when input x is 1, go to A. 1, okay, go to A. Okay. One more example. Okay, this single pulse. Okay, the output Z, okay, will be 1, okay, for 1 clock period when input x is 1. And then the output Z will be 0 until the input become 0 and then change to 1 again. Okay, let's consider this timing diagram. Okay, I want to design the circuit that when input x is 1, okay, clock tick, okay, first clock tick at here, x is 0, nothing change, output still be 0, clock tick at here, x is 0, output Z still be 0, clock tick at here, x is 1, so now output change to 1 for 1 period of clock, and then back to 0, okay, and then clock tick x is 1, nothing change, it's but wait, right, for x become 0 again, become 0 before change to 1 again at this point of time, at this clock tick, then output Z, okay, become 1 for 1 period of clock again. Okay, this is the situation, something like when you press a switch, assume X is from switch. When the user press the switch, okay, assume when press the switch, input X become high, right? If the user still press the switch, okay, it must wait the user release the switch before, and then wait the user press the switch again. Okay, something like this. Okay, now to draw the AM chart, okay, you can do something like this. Okay, start. Okay, output still be 0. Okay, I write nothing. Okay, no any output active. And then if input X is 0, it still be state start. Okay, but if clock tick and X is 1, okay, you go to some state that output become 1, right? When X is 1, it's go to some state that output become 1 or active. That's called state pulse. After that, when clock tick, okay, go to state that output becomes 0. Let's set state wait. This state, okay, we wait, okay, wait the input become 0 again. If not, if input still be 1, then it still be this wait state. And when X become when X becomes 0, first one this point of time, X becomes 0, then it's back to initial start state. Okay, and repeat. Okay, something like this. Okay, then if you obtain this one, after that you can design the state machine, like you have got state diagram or state output table. Okay, the last one, okay, the last example, that you design binary divider, okay, with to this algorithm. For example, if your input xy is first of all 18 divided by 5. Okay, how to do the division? Maybe for this algorithm that you use this one, x minus y minus 5, then it's become what? It's become 13, right? And minus 5 again, then it's become 8, right? And then minus 5 again, and then become 3. Okay, when the result less than 5, when the result less than y, so stop. Okay, so stop. If not, repeat this one, and the answer of this divider is the number of subtraction. For example, this one is 1, 2, 3. So the answer is 3. Okay, with the remainder, this is remainder 3. Okay, so if I write with this algorithm, I start Q with 0. Q is the result of this answer, I is the remainder. While x is greater than y, x minus y, okay, and update this one to x, and increase q with 1, and repeat this until this condition is not true. Okay, and then go to this one, so x will be the remainder of the division. So from this one, how to write down the AM chart? Okay, this one is AM chart. Maybe okay, I start as state idle. For this circuit, there are input X, input Y, and start. Okay, start is control input. Output is Q, R, and ready. Okay, ready is status. Okay, output that show the status that is ready to use this one or not. If it's to be processed, and ready is not active, right? If finished, okay, the process, then it's ready to do the new one. So ready will be active now. So at state idle, okay, ready active, okay, it's ready to do the calculation. And if start is 0, okay, repeat this one until wait start is 1, then start to do the calculation. At initial state, we assign initial value from input X to some register and Y to some register, and clear the value of Q. Q will be increased, right? One increment. Don't forget that this assign is not what? It's not assign value X to register M suddenly. It must wait for clock tick, right? That means when clock tick, register M, you read data from X, register N, load data from Y, and then register Q or maybe counter Q will clear its value. So wait for clock tick. So you need to have this state wait. Okay, before do the comparison between M and N. M is from X, right? N is from Y. Okay, to check that X is greater or equal Y or not. Okay, this one. If yes, okay, M minus N, okay, apply to register M, okay, and count up, okay, one increment at register Q. Okay, again, this one not update suddenly, right? For example, this one may be used load, right? Just load signal active, but not load suddenly. It must wait for clock tick. This one also count up, right? Just enable of counter active, but not count up suddenly. It must wait for clock tick. Okay, that means when clock tick into state wait, and the value of reduce the M and Q will be updated. And repeat this one until this condition become false. Then you can go to finish state. When you finish, ready can show the, can be active, and prepare to load data from M2R as the remainder. Okay, this one. So how many states of this one? 1, 2, 3, 4, 5. 5 states. That means you need to use at least 3 flip-flop, right? 3 flip-flop. Okay. For 2 flip-flop, you can it can represent 4 states, right? For 3, you can use for 3 flip-flop is represent up to 8 states. So anyway, I try to reduce number of states, but observe that during you wait, the input start become 1. You repeat this one, right? Repeat this one. Okay. During the repeat this state, actually you can assign initial value to this register, right? So I move this register assignment to this idle state. Okay, during repeat it, you can clear. You can assign value x to m. You can load data from right to n. Okay, this one. So you can reduce. You can merge this state and this state together. And now 1, 2, 3, 4. Okay, you have 4 states. That means you can use only 2 flip-flop to implement this machine. Anyway, from this one, because the result of the vision is stored at Q, right? At Q, when it's back to here and go to here, when clock tick again, what happened? The counter or just Q is clear its value. I mean the result of the division is gone. Okay, disappear. Just for some 1 or 2 clock tick. It's not so good, right? So in order to keep the answer, in order to keep the answer of the division, so let I add more register Q, okay, to keep the result of division. Okay, now if I prefer this aim side, then I will analyze what kind of device need to implement this state machine. At first, based on this behavior, first of all, M should be registered, right? Because you load or keep the data from X at this state, either or this state. Okay, choose M as register. N also register. Q 0 at here and 1 equivalent at here. So Q should be counter. Okay, Q should be counter. And the circuit choose comparator to compare M is greater than N or not. This is some kind of combinatorial circuit. Okay. For example, if you want to compare that if this one is 3-bit, for example, 3-bit value, M to M 1 m0 is greater or equal to n 2 n1 n0 or not. Okay, you must compare that. How to compare? At first, let me to this one. Okay, this one to compare. At first, let's consider that is equal or not first. This one and this one. Is it if it's equal together, right? How about this one and this one? No, right? It's different. Okay. To check that it's equal or not, you may use XNOR gate. Right? XNOR gate. Because the output of XNOR will be 1 if its input are the same. Okay. So this one also. Okay. To check that it's equal or not. If all of these NOR XOR gate, XNOR gate output all is 1, that means this number and this number are the same. Okay, so you use AND, right? AND gate to check that all of this is 1 1 1 or not. Okay, or you can check it's different or not by check if one of these different, that means these two number is different or not equal. Maybe you may use XOR gate, right, to check this bit different or not, this bit different or not, or this bit different or not. If one of these give logic 1, one of these, that means these two numbers is different, right? So you use what? OR gate, okay, to check that one of these is 1 or not. If yes, output of OR gate will be 1. We show that this number and this number are different. Okay, this is for check different or equal. If you want to check it's greater or not, for example, if this one is 1 1 0 and this one is 0 1 1, okay, we may take this one, right? MSB first. If this is 1, this is 0, that means this is greater than this one. Okay, if it's 1 1 0, it may be 1 1 1, something like that. You must check this one equal or not, this one equal or not, right? Okay, so to check that this bit is greater than this bit or not, maybe you may check. For example, if you have M2, M3, M0 compare with N2, N3, N1, N0. If you want to check that M is greater than N or not, okay, you should compare this bit first, right? That M is 1 and N is 0 or not, right? So you can write down M and N prime for the bit. Okay. If M2 is 1 and N2 is 0, so this condition becomes true. M is greater than N, right? Or if M2 and 2 are equal, namely M2 XNOR N2 is true, then you must check, right? M1 and N1, okay, is 1 0 or not, right? If yes, okay, M is greater than N, M1 and N1 prime. Or the last one, It's possible that m is greater than n by m2 equal to n2, m1 equal to n1. And you must check m0 is 1, n0 is 0 or not. So you can write down the condition like this. m2, n2 equal together, x not together. And m1, x not n1. And m0 is 1, n0 is 0. Okay, they want to check that m is greater than n. And if you want to check that m is greater or equal to n or not, you just add more condition, right? The condition of m equal to n. Namely, you check m2 equal to n2, m1 equal to n1, and m0 equal to n0, something like this. Okay, it's just the equation, okay, or expression to check that m is greater than n or equal or not. So it is one of combinatorial circuit. Okay, back to this slide. Subtractor also you use it, right? M minus n. This one also combinatorial circuit. Okay, and R and W also register. So now from this, you can write down the data part. Okay, data part or data unit. For example, register n. Okay, you load data from y. I mean read data from y. This is register n. It's operated by clock, right? But wait for clock tick. Okay, and you need control signal load n to enable. Okay, if load n is active, when clock tick, it will load data from y. Okay, and its output is n. And for m register m. Again, have control load enable input load m. When clock tick, if load m active, we load data from what? In this state, load data from x. But this state, load data from m minus n. That means you must use multiplexer, right? To select that. At this state, you load data from x. But at this state process, you read data from subtractor circuit, m minus n. Okay, use multiplexer. Namely, at this state idle, the value of select should be 0, right? Okay, to feed data from x to register. And at state process, select signal should be 1. Okay, to feed data from subtractor to register. Okay, what else? Register R, read data from M, right? Then you connect output M to register R. Okay. And register R have control input load R. Okay, which should be 1 for state finish. Okay, and Q is counter. Q is counter. Okay, at state idle, clear counter should be active. Okay, at state process, okay, counter, okay, should be active. And state W, okay, receive data from Q. Then you connect Q to register W. Okay, something like this. So now you will obtain data path, okay, of the state machine. Well, now how to control this signal. Okay. How to assign or apply this signal? For example, at this state, load M should be active. So it's active high, then it should be 1. At this state idle, load N also should be 1 at this state idle, and clear Q counter should be 1 at this state, right? And for state weight, for example, the one not active should be 0, 0, 0, okay, something like this. As state process, load M active again, it should be 1 at here. As the process count up, it should be 1 at here. So you need to use more circuit, okay, to control this kind of signal. Okay. That means you need to use control unit. Okay. This control unit you provide this control signal and output. Okay. Okay, now let's design control unit. Okay. From AM chart and data path, actually you can design control unit easily by copy this AM chart. Okay, copy the structure or the flow of the chart. You can change a little bit. For example, this one X, okay, value X load to M. That means load M must be active. Okay, Y to N, that means load N must be active. Okay, clear Q to 0, that means you must clear Q. Okay, then clear Q must be active. Okay, at this state again load M active and count up. Okay, up active and select. Okay, select this from multiplexer. Okay, at this state, as state process, you want to load data from subtractor, and because subtractor connect to address 1 of multiplexer, so select should be 1 for this step. Okay. Okay. But at this state, okay, write nothing. This state select is 0. Okay. Load X to M, right? X to M. Okay. Select signal is 0 at this step. But because it's not active, so we don't write it in this state box. And for this one, already complete, right? Select active, load active, up active, and state finish. Okay, output ready active. To load M to register R, that means load R must be active, and load W must be active also. See. Okay, the next step, when you get this control unit, okay, AM chart for control unit, after that you may assign, okay, do state assignment, assign the state variable value for each state. For example, idle for assign to 0, 0, wait 0, 1, process 1, 0, and finish 1, 1. After that, at state idle or 0 0. Okay, Q1 Q0 is 0 0. When clock tick, it maybe go to state idle or go to state wait. It depends on the value of start. Okay, start is input variable. If start is 0, the next state is 0 0 or state idle. If start is 1, go to state wait, okay, or 0 1 for start is 1. At state wait 0 1, when clock tick, may go to state process or state finish based on the value of this comparator. Okay, if this comparator give the value of 1, so it's go to state process 1 0. If not, go to state 1 1. And the next state, if the current state is state process 1 0, when clock tick, it's go to state wait, right? No input condition. It's always true. Okay, just wait for clock tick. Then go to state wait 0 1. This state also for state finish. Okay, it wait for clock tick. Then it's back to state idle. Okay, now from this table, you know that you use 2 flip-flop, which may be the flip-flop, right? 2 D flip-flop, and one is Q0 and Q1. Okay, and so you want to decide what? Circuit G, right, and circuit F. Okay, both are combinational circuit. Okay, for this example, let's use multiplexer and decoder to implement this combinational circuit. Okay, by this one. For circuit F or next state logic, I use multiplexer. Okay, let's consider Q1 star. Okay, when clock tick, Q1 star will read data from D1, right? So let's consider if the current state, okay, is 0 0. Okay, I use multiplexer by using Q1 Q0 as selected signal. So if the present state is 0 0, that means it will read data from 0 0, okay, position at the 0 0 of multiplexer. Okay, now Q1 star is 0 0, right? That means D1 should connect to 0 when Q1 Q0 is 0 0. So you want apply or connect 0 at here. Okay, now just focus only on Q1. Okay, at state 0 1, okay, Q1 is 0, Q0 is 1. You read data from this, and at this state Q1 star is 1, right? Constant 1. So you connect 1 at here. And at state 1 0, when Q1 is 1, Q0 is 0. Okay, no any condition. And the next state, the value of Q1 star is 0. So we must apply 0 at here at the address of 1 0. Okay. And the last state 1 1. When Q1 is 1, Q0 is 1. When clock tick, Q1 star must be 0. So you must apply 0 at this position. Okay, that's all for D1. How about D2? When clock tick, Q0 or Q0 star will update with the value of D0, right? So now let you consider Q0 star. When the state machine is on state 0 0. Okay. The next state, the value of Q0 star is 0 1, same as the value of star 0 1, right? So you apply start signal at here, and at state 0 1, when clock tick, Q0 star become 0 1 with different or opposite to the value of comparator. So you apply invert of this comparator at this position. And at state 1 0, okay, when Q1 is 1, Q0 is 0, go to state that Q0 is 1, so you apply 1 here. And for state 1 1, okay, the next state and the value of Q0 star is 0, then you apply 0 here. So now you can complete this part of the circuit, namely you complete circuit F. Okay, next state logic now. Okay. How about output logic, circuit E? Okay, now I use decoder, okay, decoder to implement this part of the circuit. Okay, because the state variable is from Q1 Q0, right? And the output, okay, for example, okay, let's consider this one also. The output ready will be active at state idle and finish, right? Or when Q1 Q0 is 0 0 or 1 1. When Q1 Q0 is 0 0, Y0 active, or when Q1 Q0 is 1 1, Y3 active. So you just all these two cases together by using OR gate. Okay. Sorry, this one. Sorry. This one. Okay. Then it's ready signal. This and this. And for the next signal, load M at here and at here. Okay. At state 0 0 or 1 0. Okay. When Q1 Q0 is 0 0, Y0 active. When Q1 Q0 is 1 0, 1 0 is Y2 active, right? That means you combine these two cases together by using OR gate for load M. And the next signal, load N. Load N will be active, that will be this, right? This state. Okay. And clear also, okay? Only this state. So at state 0 0 or Y0 active, it should use as load N and clear Q. And what else? Select. Okay, select will active generally this state 1 0. Okay, 1 0 or Y2. Okay, Y2, and this state up also active. Select and up. Okay, connect to this Y2 and ready already. and load R and load W, okay, will be active just only this state 1 1. When Q1 Q0 is 1 1, Y3 active. So you can use this Y3 as load R and load W. Okay, that's all for today's lecture.